Okay, so it's November 6th, 2024. Yeah, that November 6th, 2024. And I've always been interested in starting a YouTube channel, and I've had some ideas of things I wanted to talk about. And one of them is programming, and today I find myself needing a distraction to do something creative. And so I decided to start my channel. And so today, I'm working on my first programming video. As you can see, my cat likes to lay on my desk when I code. So her name is Brioche. And so I'm going to call any programming videos, especially if she's around, Programming with Brioche. And so yeah, that's it. So let's get started. As soon as I get my hand back, hold on. Ouch. Okay, so this thought came across my mind when a particular PR, or I noticed a PR at work that did something like this. And so the idea is that the author of the PR wanted to take a slice and then turn that slice into a set of sort of sub slices. So you pass it a slice and you pass it like a stride or an N, and it would take that slice and return a slice of bucketized slices, or maybe chunked is a good word for it. So you pass it a slice and then you get it back a slice of slices, and each sub slice is of size N, or at most size N. And so yeah, I'm going to call that sort of a chunking operation. Yeah, so I saw a PR that does something like that. The code was a little bit different, but I'm going to kind of type up what the gist of it was. So let's make a module. And so what it did was it took a particular type, but I'm going to use type parameters now. So I'm going to just say chunk t any, and let's say it takes a slice, and we'll call it s of type a slice of t, and then some stride, which is an int, and returns a slice of slices. All right. So the first thing we want to do is create a result of type slice t, and maybe iterate over a slice. So while I equals 0, we don't want I to be greater than length of s, and we want to increment I by stride. So I plus equals stride. And so now we could append to our result slice. Let's see. We want to reslice s. So say s starting with I up to I plus stride. Yeah. And then return the result. All right, so now the problem with this is that if the length of s is not evenly divisible by stride, this will cause a panic when we kind of walk off the edge of our slice. So we will have to do something like the min of I plus stride and len of s. Okay, so I'm pretty sure that's it. So that's a pretty straightforward function. Let's test it out. So if we have a slice of ints, so we could say ints equal int 1, 2, 3, 4, 5, 6, 7, and maybe we could say t.log f %v chunk ints, and let's say 2, and then maybe we'll do another one in 5, and then 8 or 9. There's a typo, but I'll roll with it. Okay. So what I hope is that the first one would yield about 3 subslices, the second one 2, and the third one 1, right? All right, great. So just as anticipated, we have 4 subslices, 2, and then 1. So now, there's nothing wrong with this at all, except that we are allocating each one of those subslice headers. So we're not like copying the data, but we're allocating at least the slice header that contains the length, the capacity, and then a pointer to the actual backing array. Let's see. So how do we visualize, or how do we show how much memory we're allocating? What we could do is benchmark. And maybe iterate from I equals 1, I is less than maybe 100,000, and then I times equals 10. And maybe we'll say less than or equal to 10,000. Not sure why that's complaining. Oh, less than or equal to. There you go. All right. So what I'll do now is in a subtest, maybe t.run func s_printf %d I will be the name of the test. And func t testing t. And so now let's just make a slice event. It doesn't matter what's in it because the contents of the slice doesn't affect like how it's chunked. So maybe we could say like s equals make slice event, and we could set the length and cap to I, yeah, and then for range over b.n, and of course this needs to be a benchmark. All right, so for range over b.n, and this needs to be a benchmark. There. Sorry about that. All right, so now for range over b.n, we could simply say chunk s, and we'll just divide into 5 for now. And I think what we could do is go test bench and run each benchmark. Great. But what we want to do is bench and then say bench mem. All right, so as we can see, the number of bytes we allocate per operation increases as the number of elements in our slice increases, right? So eventually, you know, I could just sort of eyeball this. It looks like about 22.8 bytes per node that we're, or per list element that we're allocating when we get to the 100,000 side. And of course, when we're at 1, we're talking about 24 bytes per operation. So that's pretty consistent, right? It does, so here we have 10, let's see. Anyway, yeah, it seems to fluctuate. There's the underlying mechanics of the slice and how it allocates exponentially and then falls off at a certain point. But we'll kind of hand wave over that, but just observe that clearly the amount of memory we need increases as the size of the slice that we're chunking increases. Another factor that'll impact that is like the number of elements in the chunk as well, right? So, for example, it goes without saying that for longer slices, if we ask for fewer slices in the chunk, it's going to have to allocate more slice headers, right? So, for example, if we said 2, what I hope we see is that the number of bytes per operation increases. And yeah, it's pretty apparent. So already we're in the 360 bytes. So here we're already talking about This is 10,000. I might have to break out the calculator for this. So bytes divided by, I'm sorry, 100,000. So yeah, we're talking still 63 bytes. All right. So less than, or it's more than 20, what do we say, 27 bytes per operation. So anyway, yes. Bottom line is that this takes memory, or this consumes memory. So the thing that I thought was interesting is that the new range function feature would allow us to iterate over these chunks, because ultimately that's what we're doing, right? The purpose is so that we could create these chunks and then range over those chunks and do something with those chunks. But instead of pre-allocating them, if we use the range function feature that I think is now in like 1.23, the nature of that transformation of the range body into a function call, and hopefully the fact that we can inline that function call actually, let me rewind all this. The nature of that transformation of the range body into a function call will allow us to yield each of the chunks to the body without having to first build an entire slice of whatever size that we need. The point about that is we might be able to say something like, I'm just going to call this, we'll call it batch. Yeah, I like that. Okay. So batch of T any, S slice T, or of type T, and then stride of int. And so since this is going to return a range function, we're going to return a func that takes a function of type slice of T and returns bool. And that function doesn't return anything. And so I probably could have said iter sequence of type slice of T, like that, I think. Does that work? Yeah. All right, so now what I could do is return a func a type that will be past the yield function. That is a function that accepts a slice of T and returns bool. And in here, do something similar, right? So instead of appending to a result, I could just copy that inner loop. And if not yield, si min I plus stride len s. All right, then return. Let's see. So return func. Yeah, there we go. So let's test that. First, we could say like func test batch T testing T. And now we could say ints is that, and for maybe batch equals range over, or we could say maybe B is range over batch, ints in batches of 5, and we could just say t.log f %s or %v b. All right. And now if we run tests, we'll say just run all verbose. Great. So test batch does, I think, what we expect, right? So yeah, batches it in 5s. Let's see what happens if we batch it in, or do batches of 2. Great. So it does what we expect, right? So now we could range over it, but notice that we haven't performed any allocations. In fact, we could write a benchmark. I'll say benchmark batch B testing B. And then we'll do something similar. So we'll iterate over batch or over slice sizes of up to 100,000. But instead of calling chunk, we'll simply run our range loop. maybe even without a body. And we want to pass it S. And we could even discard the result. So just make sure that we're comparing apples to apples. We're chunking in batches of 2. Great. So let's run our benchmarks. All right, so chunk, we're allocating 24 bytes per op for one chunk, 360 for 10. All right, so now batch. Check that out. 0 allocations. But also notice that the overall runtime is a lot lower. Not sure what just happened there at 100,000, where we got 110 bytes per op, or even 1 for 10,000. But or I guess the upshot here is what I'm observing is the efficiency and the optimizations you can get from using range functions over using sort of temporary slices in the way we typically do. And so you may be wondering, okay, well, maybe we could do this over a slice, or over a channel. So let's try that. Let's say maybe Func Chabatch. Yeah, like that. So I'm just going to copy this entire thing and say Chabatch. That will return a chan of type T. I'm sorry, a slice of type T. And likewise, instead of pre-allocating, or instead of allocating a bunch of, instead of appending to a result, we'll just maybe say chan equals make chan of type slice of T, go func body, and return ch. And so instead of yielding that data to kind of like the inner, or the body of the range loop, we will simply sort of send this subslice over our channel. Yeah, okay. And so let's benchmark that. Oh, let's make sure we close our channel too. All right. So we'll call that benchmark Chabatch. And then say for range Chabatch S2. Whoops. We'll do this. Yeah. All right. So now let's run our benchmarks again. So there goes our chunk. There goes batch, which we see allocates almost nothing. And then Chabatch over channel. So there is this, it looks like a constant allocation. Then we get that, then we get a little bit at 10,000, 100,000. Still not sure about that. I assume that constant, or some of that allocation, is coming from the channel that we're allocating. What's nice is that the memory footprint is constant. Not quite 0, but it doesn't like kind of increase almost exponentially as the number of items in our slice increases exponentially. But its runtime performance is much worse, because part of the process of like communicating that result over channel means that essentially there's a runtime kind of context switch, usually some locking and blocking on the send and receive side of the channel. So we're dealing with kind of communicating across 2 go routines, and so all the sort of runtime mechanics that are required to make that happen kind of impact our runtime efficiency. Whereas when we use a range function, we get this nice basically like a literal function call that again can be inlined. In fact, I'm wondering if this is in fact inlined. So if I say go I can test C dash DC flags equals dash m dash m dash m dash m, and we'll pipe that to more. Obviously, you could inline the actual benchmark code. Oh, so it can't, sorry. But it cannot inline Trebatch, of course. Oh, it can't inline batch either, function too complex. Oh, it's only 4 over our budget. But let's see, so chunk shape int. And it actually can inline. Oh, so it does, I'm sorry, so it does inline chunk. Which one's chunk? Ah, okay, well, so chunk is even inlined, whereas batch isn't. Let's see. Oh, it can, I'm sorry, it can inline batch. Here it goes. It only has a cost of 17, so it's not even nearly as complex as chunk. So yeah, it is inlined. And so we get that nice efficiency from having essentially a ranged loop turned into a function call that then can be inlined, right? So that's it. That's all I got. So my takeaway from that is that in the future, you know, whenever, like in particular, whenever on my team we adopt Go 1.23, we can use techniques like this to reduce our memory footprint, reduce the number of allocations, reduce the garbage collector pressure, GC pressure, and overall, I think get a lot of wins out of using range functions. So that's all I have, right, Brioche? Oh well, she's gonna bite me. Can you say bye, Brioche? No, maybe next time. All right, see you later.